So yeah, this time we'll be talking about ensembling and mixture of experts models. And the basic idea here is that many different models exist that we could be using. Um, and there's a number of reasons why we could have different models. We could have different architectures, or we could have different training data or other things like this. And this results in a different, modeling distribution that we have. So for example, we could be initializing a model randomly with 7 billion parameters, and then pre-train it on a certain pre-training data distribution, get llama 7b. We could be doing another 7b model, slightly different or similar architecture, get Mistral 7b. And then we could have a 70b model, get llama 70b. And then further, we fine tune it. So we could fine tune Llama 2 7b instruct or Vicuña 7b. We could be fine tuning Mistral to be the instruct version, or we could have somebody else do News Hermes Mistral and have an instruct version here. And so, all of these will be a bit different. They'll be good at some things, they'll be less good at other things. So the idea is that we might want to take all of these different models and somehow combine them together in order to get better results in whatever way we define better. So model ensembling is probably the simplest way to do this. And it combines together predictions for multiple models. And it's kind of a general idea, but the easiest way to do it, no, I wouldn't say easiest, but like one simple way to do it is you take two models. This says LSTM because these slides are old, but nowadays it would be transformer. We calculate the representation from both, we make predictions, and we combine them to get a combined predicted output. And the reason why we do this is if models made the same errors, this would not be very helpful, but models make decorrelated errors. So their errors tend to be less consistent than when they get it correct. And this allows you to get better accuracy by combining multiple models together. Another thing is models tend to be more uncertain when they're about to make errors. So when they get it right, they'll have the probability tend to be higher than when they're about to get it wrong. And so because of that, that allows you to pick the correct answer more often than you pick the wrong answer. And so that can smooth out the idiosyncrasies of different models. So one standard way of doing this is linear interpolation. And linear interpolation, basically what you do is you take the weighted average of M model predictions like this. And I wrote this in a probabilistic way. Sometimes you also write this in a, with this just being a parameter. But basically what you do is you calculate the probability of using the model at the current time step multiplied by the probability of the next token at that time step. So probability of the token according to model M and the probability of model M. And as I just said, the second term we often set to a constant independent of context. So you'll often see it look like something like lambda M E M Y YG. What could? Yeah.
Is it always like the final output and combining the final output, or do we sometimes use intermediate stage, like just the penultimate stage?
I will talk about that in a bit. Not directly answering that question, but answering something close to that question, and then maybe I can answer that question when we get there. Any other things? Okay. Another common option is something called log linear interpolation. And here, what we do is instead of combining together the probabilities themselves, we combine together the log probabilities. And so we have the log probability here, we have some constant here, and we sum them together. And then after we've done this, we take the softmax to renormalize. So this is an interpolation coefficient for model M, and this is a log probability of model M in a normalization constant, normalization term. So I didn't do any softmax or anything like that here. Does anyone know why I didn't need to do that, or can anyone guess why I didn't need to do that?
So weights are less than one only, so the probabilities will always be between 0 and 1.
So the weights are less than one. The weight could be one here actually, and if all of the other ones were 0, but yeah, any other things? Yeah, so the probability of this probability over all the tokens will sum to 1 for all models. This will also sum to 1 for all models. And so if you take 1 times something that sums up to 1, and you do the sum over all the models and the sum over all the tokens, you will also get something that sums up to 1. So as long as this is a probability and this is a probability, actually you'll get a probability. However, that's not the case for this. So in this particular case, you will need to renormalize and take the softmax. Cool. So which one of them do you want to use? This is not super obvious if you're not familiar with this already, but you can actually think of it as kind of like logical operations. And the linear interpolation, where you just add together the probabilities, is kind of like a logical OR. So the interpolated model likes any choice of model that gives a high probability. So if one model gives a very low probability and another gives a high probability, then you'll still get a relatively high probability. And you can use this with models that capture different traits. So if you have one model that's really good at English and one model that's really good at Spanish, you could combine those two models together and you would get a model that's good at like both English and Spanish. This is also necessary when any model can assign a 0 probability, because the log probability of 0 is negative infinity, and that means you would assign a 0 probability to anything if you use log linear interpolation. So if that's the case, you need to use linear interpolation. Log linear is kind of like a logical and the logical and means that the interpolated model only likes choices where all of the models agree. So all of the models have to give a reasonably high probability, otherwise you're going to get a low probability. And it's good to use this when you want to restrict the possible answers. So if you want to have, like, for example, a model that assigns really low probability, it's not a very strong model, but it assigns very low probability to any toxic speech. So you want to prevent it from giving you any toxic speech. Linear would not restrict anything, but log linear could. So that's another situation where you can use it. And just to like maybe give this intuition a little bit more, let's say we have an example where we have word A, word B, word C, and word D. If the So if we have model 1 and model 2. So in this particular case, if you had a log linear model, the log linear model would like this one the best because it would be basically -2 and -2, and then you would renormalize and you would get probably something, sorry, the log linear, if you take the log probability of this, it would be -2, -1, -10, -10, and -2, -10, -1, -9. And so if you take the log linear model, this has no very low values, so this would get the better scores. But if you added these two values together and divided by 2, you would get something, this is basically a trivial value, so you would get something like 1 divided by 2e. And 2e is larger than e squared, so this would, one of these two would actually get the highest probability. So that's the difference between like log linear and linear interpolation. Log linear would like this, whereas linear would like one of these two. That clear? Okay, sounds good. So this is how you combine models together. Usually what we do is we take two models that we kind of like, and we combine them together to get a stronger model than either of those two models. But another thing that you can do is you can use models as negative evidence and try to bias outputs away from using particular models. So for example, if we're using log linear interpolation, and this only really works with log linear interpolation because in linear interpolation, you generally use a probability, but in log linear interpolation, you can actually use a negative interpolation coefficient. So here we have a core model. And so this is like the model that we want to adjust in some way. And then we have a positive model and a negative model. So we want to modify this model in some way to bring it closer to this one and farther away from this one. And so to give a couple examples of this, there was this paper, this is one of our papers, and we had a machine translation model. And the machine translation model was trained on text that is parallel between two languages. So we can't get very much of this text because it needs to be parallel. You need to have text in both languages. Then the negative model is an out-of-domain language model. So this out-of-domain language model actually could be trained on the same data that the machine translation model was trained, but only in the target language that you want to translate into. And then the positive could be in an in-domain language model in the target language that you want to translate into. So like, let's say we have a machine translation model trained on news text, then we would have a language model that was trained on news text in the target language. Like, let's say, we're doing English to Chinese, it would be Chinese news text. And then the positive one would be in-domain language model. So this could be something like medical text in Chinese or something. So that would move you away from being a news translation model and towards being like a medical translation model. Another example of this is something that was called Dexperts. And here, the core is a strong language model. Then the negative one is a weak toxic language model. So this is a language model that, is trained on like bad forums on Reddit or something like that. And then the positive would be one that was trained on, like benign text that's not toxic. And so that could move you away from generating toxic text and towards generating not toxic text. And so this is just a special case of log linear interpolation where you have positive lambda on this model and negative lambda on this model. Cool. Any questions? Yeah.
Why can't we just use the core and the negative models?
Yeah, so why can't you use the core in the negative models? So the reason why you wouldn't want to do that is, let's say you were just subtracting out Chinese news. You were just removing or lowering the probability of Chinese news. that might lower the probability of Chinese in general, right? So you would be getting something that's like less natural Chinese. And so the difference between them is kind of the difference between the domains, for instance. Yeah. Yeah, so when you do linear interpolation of probabilities, one condition for this working is that this probability of the model has to be a probability itself, and probabilities have to be between 0 and 1. So there are probably ways that you could readjust it, but kind of the more natural way to adjust it is just to redo the softmax on the logits. Another reason why it wouldn't work if you did it just on probabilities is, again, like as I mentioned before, doing probabilities isn't a great way to like prevent it from outputting low probability stuff. So yeah. Cool. Any other? Okay, let's go ahead. Cool. So this is ensembling. It's very useful. It's actually, if you want to increase your accuracy, one of the easiest ways to do it is to ensemble different models together. So if you, for example, want to get a good grade on an assignment where you want to get good accuracy, it's one way you can do it. But the problem with it is cost. So simple ensembling is expensive. It requires running multiple models at the same time. And so this means you have to do n times the amount of computation, but you also need n times the memory. And this is even more of a problem, basically, if you're using a single machine. And so we want to think about if there's any way we can do this more easily and combine together multiple models. So actually, before I get into the next thing, one thing I should mention is one way that you can do this really easily without any of the fancy stuff I'm about to talk about is just generate outputs from all of the models and rescore them. So like, for example, for assignment 2, if you wanted, like, let's say you train 5 models and you want to get the best possible accuracy, you could generate n best lists or sample from the 5 models and then rescore them by calculating the probability according to all of the 5 models and average them together. And that's, I wouldn't say it's guaranteed to increase your accuracy, but it's one of the most consistent things I've seen in like my work is that this sort of method can increase your accuracy. But let's say you don't want to do this. Let's say you don't want to spend all the computation time. One very effective thing that people do is parameter averaging, or somehow combining together the parameters of all of the models. And this is a cheap way to get some of the good effects of ensembling. And you take the average of the parameters of multiple models. One way that you can do this with like basically virtually no additional cost is you save multiple checkpoints and you write them out several times near the end of training and take the average of the parameters of all of these checkpoints. And this is good because stochastic gradient descent, where we're updating the parameters every time, it's unstable. And one way to improve the stability is just by making larger batch sizes and stuff like that, but that slows down training. So this is one way to kind of get the best of the both worlds. It stabilizes your training at the same time as not really slowing it down that much. So this is definitely something you can do. Another thing is merging together multiple fine-tuned models. And this is actually pretty popular. It's so popular that on the Hugging Face leaderboard for open models, they had so many models that were merged together that eventually they like disabled displaying them by default because it was like polluting the leaderboards. So this is also a very popular method that a lot of people are using. So one thing I should mention is that these methods only really work on very related models. So for example, you could average together or merge together these models that were trained from the same pre-trained model or these models that were trained from the same pre-trained models. But you couldn't necessarily do kind of like Vicuña and Nuss Hermes Mistral at the same time. And there's a couple reasons why you couldn't do this. Anyone have ideas? Yeah. Yeah, it's likely that they're in different local minima, so you might get a much worse model. So this is definitely correct. Even going a little bit beyond this, in neural networks, you can permute any of the parameters. So any of the parameter matrices, you can permute them essentially and get exactly the same result. So what I mean by this is like there's no within the transformer, there's no inherent meaning to node number 1 or node number 70. And so you could just like swap node number 1 and node number 70 and get exactly the same result, as long as you swapped all of the like appropriate elements of the matrices, of the weight matrices and stuff like that. So because of this, it's quite possible that Llama 2 7B and Mistral 7B have very similar nodes, but just in one of them, it's node number 1, and one of them, it's node number 70. And if you combine them together, they basically become meaningless. So that, this permutation could cause problems. And then even separately from that, being in separate local minima is still an issue. Another even simpler thing is Llama 2 7B and Mistral 7B have slightly different architectures. So it doesn't really make sense to average things that have different architectures. But moving on to methods that you can do, like parameter averaging is the simplest one. There's also this paper, Model Soups, that examines different strategies for doing this. One is uniform averaging, which is more or less what I just talked about. And then the other one is greedy averaging. And what they do is they add 1 and keep it if that addition to the average improves the accuracy. And this was, I believe, done only or primarily on image classification models. So this is like image net accuracy. But what you can see is the green ones are all trained with various hyperparameters. The blue one is if you do this uniformly. And then the purple one is if you do this greedily. And the way you look at this is essentially, this is image net accuracy, and they did the greedy merging based on ImageNet. So they basically decided whether to add it or not based on the ImageNet validation set. And then they have the uniform one. So the uniform one did significantly worse on ImageNet. It got 80, while the greedy one got 81. But they also tested it on out of distribution data, and they found that essentially this greedy merging strategy might be overfitting to the ImageNet data. So actually just combining all of them together did slightly better on these out of distribution data sets. Another thing is they also demonstrated that averaging is correlated with ensembling. Sorry, that should be ensembling, not resembling. But so this is the 2-model soup, and this is the 2-model ensemble. And they demonstrated that in most cases, the combination or the parameter average is very similar to the ensemble. But there's a few cases where essentially the 2-model averaging just does much worse than the 2-model ensembles. So there are some cases where, as you mentioned, there's a poor, each one is probably in a local minimum where you have relatively high accuracy. And then you take the middle of the two and you get something with low accuracy. So that is a danger. That does happen in some cases, even when the architectures are the same or the initialization is the same. So. Cool. Everything okay? Any questions? Okay, cool. So the next thing I'd like to talk about is task vectors. And this is a kind of interesting idea. The basic idea is you start out with an initialization. And the initialization, the difference between the initialization and the final trained model is something they call a task vector. And they demonstrate that you can use the task vectors to do adaptation. I mean, it's it's kind of a tautology that if you add the task vector into the original model, that you get the downstream model. So if you just add it, it works. But they also demonstrate some other things, which is like you can forget the task by subtracting out the task vector, similar to what I talked about before, with subtracting out the probabilities. You can also compose together two task vectors to get a model that is better, that can do both tasks. And you can improve generalization by further doing kind of the adding and subtracting and stuff like this. And there's other methods that take this step further. So one of the adaptation strategies is this one called ties. And basically what they do is they look for places that conflict. So for example, here, this yellow direction is conflicting with the pink and the purple directions. And they basically take the one that has the highest magnitude here. And they demonstrate that this works better than just averaging them together, because if you average them together, this would, go down a bit, despite the fact that it's really important for solving this particular task. So this is another method that has been used. And in terms of software that people use to do this, there's a piece of software called MergeKit that's relatively popular. And this implements a bunch of different methods for model merging on a bunch of different kind of models as well. And it's compatible with Hugging Face, other things like that. So you can take a look at that if this is interesting to you. So a final thing from our Nobel Prize winner in physics is ensemble distillation. Ensemble distillation, the basic idea is parameter averaging only works for models within the same run. You might still want to distill. Sorry, you might still want to gain some of the advantages of an ensemble without like doing that, or getting a smaller model that gets some of the advantages of the ensemble. And knowledge distillation basically trains a model to copy the ensemble, and it tries to match the distribution over the predicted words. And I think you already had the distillation, the class where we were talking about distillation and stuff like this. But the reason, kind of the intuitive reason why this is good, even for the case of ensembling, is if you're just fitting like the one hot distribution for a language modeling task, then you get only one piece of information from any token that you're fitting, right? You get to see that, like, oh, this is the token I observed this time, but in reality, there might have been a whole bunch of tokens that would be useful in that particular context. And so the ensemble gives you a very good prediction of the probability that you might see over the context. And so what you do is, instead of fitting the one hot distribution, you actually try to fit the probability that the model, that the ensemble would have given you. And this increases accuracy notably over just fitting the one hot vector. Yeah.
Target is still to reduce the model size.
So the goal of doing this, of ensemble distillation, is either to reduce the model size, or it's to take an ensemble and fit a single model that matches, nearly matches the ensemble in performance. Yeah. Cool. Okay, so this is it for ensembling, and I'd also like to talk about mixture of experts models. And mixture of experts models are very popular. We know a lot of the biggest models that are used nowadays are mixture of experts models, a lot of the biggest public models. And there's quite a bit of speculation that a lot of the private models are also mixture of expert models. So I think this is used pretty widely in kind of the largest models that we have available. And the basic idea underlying this is sparse computation. And sparse computation if we think about what happens when we do a scalar tensor whenever we multiply a scalar by a tensor, the result is guaranteed to be 0. So we have 0 times any size of tensor. We know this is going to be 0. So we don't even need to calculate anything leading up to the calculation of that tensor, right? And so this can happen in many parts of the model. So this could happen to single rows in a matrix multiply. So for example, actually, I think I might have it on the slide. Yeah. So this can happen for single rows in a matrix multiply. It can happen for larger tensors, and it can happen for whole models in an ensemble. And so if it's single rows in a matrix multiply, some GPU operations will automatically note that one of the inputs is 0 and just not calculate that row. Sparse MOE models use larger tensors, and I'm going to talk about them. And if you have whole models in an ensemble, you just won't use that model. So GPU level sparsity is NVIDIA GPUs support various types of sparsity, and they have libraries like cuSparse and tensor cores that automatically optimize this for you. And so if you do a vector matrix multiply with a sparse vector, this vector might only have 3 inputs, in which case it will only multiply the inputs that exist and basically not consider any of the columns that don't exist. And so this is really nice if you have a part of your model that is good, generates zeros. And for example, ReLUs generate zeros, rectified linear units. If you remember, you have the x-axis and the y-axis, and so if the input is less than 0, the output becomes 0. So if you have a very sparse version of this, that can actually speed things up significantly. Recently, I think people have actually started moving away from this because of other activation functions give you better learning results, but that is something to be aware of. But when we talk about mixture of experts models, usually we're talking about sparse mixture of experts layers. And the way these work is they select a subset of feed-forward networks to actually execute when you're doing training. And the way it looks like is this. It's a little bit small, so it might be hard to see. But we have a feed-forward network, and within the feed-forward network, we have expert 1, expert 2, expert 3, et cetera, et cetera. And we have a gating network that chooses which of the experts we'll use at any point. And the way we implement this is we basically have K, where K is the number of experts we use at any time. And we have this function here. And then we zero out, or we make all of the ones that are not within the top K negative infinity, and then we take the softmax. And that means that all of the ones that were not in the top K essentially become 0. So as I said, this is used pretty widely. Just to maybe give a few examples. One famous one is this one, Mixtral, that was created by the people at Mistral. And let me... So they say 8x7b, and basically that means they have 8 experts. And if I remember correctly, they have 2 that are active at any time. So Unless somebody knows otherwise. It's 2. Okay, good. Yeah. So they have 2 that are active at any time, which means they have 4 times more parameters than the ones that are actually active at any time, saving them kind of like 4 times the compute, but still maintaining the model size. Recently, another kind of very strong model is this DeepSeek 2.5. And this one has a quite large number of parameters. I forget the actual number, but it has a very large number of parameters on the order of like 300 billion, but sorry, I can't see the screen. But on the order of 300 billion, but a relatively low number of active parameters. And because of this, the serving speed for this is like really, serving speed and cost is very low. Yeah.
Still have to load all of them on the GPU.
Do you have to load all of them on the GPU? Yes, mostly you do. And one interesting thing is that the stuff that makes this really fast also makes it really like tricky to like actually serve appropriately. So I think the DeepSeek people have really like, they really highly optimized it. So it's really fast and really cheap. But if you run it on like existing toolkits, it's like quite a bit slower. So yeah, like it means you need to do more engineering on the ML system side in order to serve them quickly. Cool. Yeah.
So it's drastically different than just having a smaller model. Like, why to have a big model just to use some parameter?
Yeah, the results are drastically different than if you had a model with only like just 2 experts and not 8. Yeah. So one question is, could you have only 1 expert? Would having only 1 expert here be reasonable? Well, okay, sorry. Not only 1 expert, I misspoke. So let's say you have 8 experts and choose only 1.
Yes, because we could adjust to the task that we want to achieve.
Yeah, you could adjust to the task that you want to achieve. That's a reasonable thing, but there's actually a problem with that. Any ideas? Yeah.
So if we have a general task that belongs to any expert, we can't average the result of multiple experts to have a more general result, but it will link to one specific domain.
Yeah, so the answer is, or like the answer that was just said was, if we have a very general task, we wouldn't be able to use like multiple experts and solve the task. That's a good point, but that's actually not what I was talking about here. To give a hint, has to do with training the model, not using the model. Yeah.
Maybe it will depend on only one strong experts and we are not training all the other ones.
Yeah, maybe it would depend only on 1 strong expert and we wouldn't train the other ones. It's very close, but I can give the answer. So basically, if you only have 1 expert, the softmax probability will become 1. And for all the others, it will become 0. And that's essentially non-differentiable. It will always be 1 and 0. So you wouldn't have any signal to learn the scaling network. You need to have at least 2 in here, because then if you have 2, then maybe one will get 75% of the probability, the other will get 25, and you can like push up the 25 or push down the 25 or something like that. So in order to learn the model, you definitely do need the scaling network to select at least 2, so you can differentiate through it. Just to use the model, it actually doesn't matter. Just if you're just using, you could have only 1 expert, and theoretically it would work, but for the reason that was mentioned before, maybe you would want to use 2 experts at once. So that might be suboptimal. So another thing is model selection. Yeah.
Because like, so does this like happen at a word level, like in transforms, in the sense that like the first 4 words maybe one expert is called and then the next 4 words a different expert, or is it like?
Yeah, does it happen at the word level? Yes, it happens every time. And it, actually you have different experts at each layer. So this in transformers, this is generally used as a replacement for the feed forward network. And you just make a really large feed forward network and select a subset of it. Yeah. Which also makes it tricky because like in your batch, in every batch, you're actually selecting different experts at every time. So you need like specialized CUDA kernels and stuff like that to make that work. Okay, cool. So next, model selection. One alternative is to select which of multiple models to use. There's a couple methods for this. There's one called model cascades. And model cascades here, there's a couple different papers that propose similar things, but this particular one is called Frugal GPT, with the idea being that what you do is you start out with a really cheap model, and based on the really cheap model, you try to decide whether it did a good enough job. If it did a good enough job, you just output the answer. But if you think it did not do a good enough job, then you call a slightly larger model and try to get the answer. And if the slightly larger model did not work, then you call your biggest model and try to get the answer. So this is, the attempt is to save money. And there's a couple different ways to do this. The one way you can do this is you can have the model like verbalize its confidence. You can have the model predict, based on its probabilities, whether its confidence is high enough. Or you can have a separate like proxy model that's cheap to run that tells you whether the output looks reasonable. So you need some variety of confidence in the output. Another option is model routing. And model routing, basically the idea is before you even start generating the output, you try to predict which model to use. And the way you do this is you run lots of models over lots of instances, and then you train a classifier to try to decide which prompts work best with each model. So both of these are options. I think nowadays model routing is actually maybe more popular. I think there's quite a few toolkits and services that allow you to do something like this. Cool. Any questions? Yeah.
Load everything into memory and then make a decision.
Yeah, it's a great question. So the people who did this research didn't load GPT-3 or GPT-4 in memory because they weren't in, they weren't in OpenAI. So this actually also would just work with, API-based models or anything else, as long as you have a way to calculate the confidence from the outputs. And similarly for this as well, like as long as you can take an input and decide which model you should be routing to, that should work. But I guess the model is loaded in memory somewhere, just not necessarily on your server. Cool. Okay. I'd also like to talk a little bit about pipeline systems. And pipeline systems, one thing that we often do is we hook the input of one system into the output of other systems. And so we take the output of system number one, and then we feed it into the input of system number two. And one example of this is speech translation. So for speech, you first do speech recognition, and then you do translation from text to text in another language. And the reason why we do this is severalfold. The first is data availability. So for example, for speech translation, there's very little speech to text in another language data compared to the amount of speech to text in the same language and text to text in another language data. So it's pretty hard to get like speech translation data, for instance. Another reason why is interpretability. So let's say you're using a speech translation system or any other variety of system. If you don't get a transcription in the language that you understand, you're not going to be able to, tell whether it's working or not. So it's also kind of important. So this is a simple method of doing this sort of thing. There's also other methods. So there's stacking. And what if we have two very different models for the same task, but predictions are done in different ways? So for example, this is an old example. There's also newer examples. But like, let's say you have a phrase-based translation model and a neural machine translation model. What stacking does is it uses the output of one system in calculating the features for the other system. So instead of just pipelining them, you take the input and you calculate output number one, and then to the model you take the input and output number one, and you calculate the like output number two. So this is kind of a general concept, but a nice kind of expansion of this concept that actually has become very popular recently is iterative refinement. And so the way this works is you take an input, you get an output, and then you take the input and output and you further try to generate the output over and over and over again until it kind of converges to something that the model is happy with. And there's a particular instance of this that is very, very popular nowadays called diffusion. And I'm not going to go really deeply into diffusion. If you're in an image processing class, you're probably very tired of hearing about diffusion because it's the standard thing in image processing. It's not super popular in language for reasons I can talk about in a second. But the basic idea here is that you take data X, and then you gradually add more noise to the data using a noising process Q, and then you use a model P to denoise step by step. So you start out with X0. So X0 is, whatever image you want to generate. You gradually add noise to it until you get like a noisy face. And then if you add more and more noise to it, eventually you get kind of just complete noise. And for images, the noise can be, for example, Gaussian noise. So images, it's actually really easy to come up with a noising process that makes sense. But this is a little bit less of the case for language. And so for language, there's a couple methods that you can use. The very simplest one that people use is they replace individual words in the input. And so you start out with like, this is a sentence, and then you get like mask is mask sentence. And then you mask out more and more of them until you just get like a sequence with all masks. But the problem with this is kind of twofold. Like, let's say you want to train a really good model for like modifying bad sentences into better sentences. This isn't only done by replacing words, right? So, very often you might have forgotten an article somewhere, or you might have split one word into two words or something like that. So a more effective method is to add noise using insert, delete, and replace operations, and then reconstruct it with a more flexible model that actually allows you to do edit operations like adding tokens or replacing phrases or other stuff like that. So there's an example like this. Yeah.
Spelling words also count as noise, if it's totally misspelled.
Yeah, misspelling words. You can add noise in any way you want. The basic idea is if you want to have a complete generative model that can generate from nothing, you need something that basically goes all the way to a like initial state. And so for Gaussian noise, this is very simple. Like you'll end up eventually with just Gaussian noise on the input. So you have a like natural zero state. For this, you have a natural zero state, which is like everything is masked. And then you need to generate like the right length of the sentence or something like that. But other than that, everything is masked. For this one, it could be like all the words are deleted or something like that as an initial state, and then you start with in empty like an empty state. But like this variety of diffusion model, one of the nice things about it is you can start with like a sentence with poor grammar, and you can like iteratively refine it into a sentence with good grammar, and you've got a model specifically trained to do that sort of thing. So, yeah. Cool. So, yeah, why don't people use diffusion models for text? My hypothesis about this is just non-diffusion language models work really well, and they're way easier to train. And there's also a more natural kind of like autoregressive decomposition of language from left to right or from, past to future. Whereas for images, there are autoregressive models that do reasonably well, but you have this weird thing where you like do autoregression on the first row and then you jump to the next row and other things like this. And so there's not really a super like natural generation order from, left to right or past to future in images. So I feel like diffusion models like help take advantage of that by kind of gradually generating it from noise kind of in a more holistic manner. So that's my hypothesis. I don't know how correct that is, but cool. So another method of iterative refinement is something called self-refine. And basically the way this works is after generating an output, you have an LM critique and improve the output. And so, for instance, if you have a dialogue, you have the model itself give feedback on whether the dialogue is good or not, and then you get a refined output. And you could do that for code as well. And like one of the really interesting and surprising things is this like actually works with some language models. So the model will generate an output, generate a critique, and the output over here will actually be better. But like one of the interesting things is when this paper came out, kind of the best model was GPT-4, and this worked with GPT-4, and it worked with virtually no other model. So like you really needed a model that was strong enough to be able to do this. And now there's a lot more GPT-4 class models, so I think they would be able to do this. And then there's also models that can do this on their own. So yeah, actually I have short slides today, so I can maybe talk about some stuff that's not on the slides. But are there any questions about this while I hold that up? Yeah, okay, cool. So this, I'd like to talk a little bit about the like results from O1, the new language model from OpenAI, and in particular, if how many people have used this on like the Chat GPT like thing? Okay, so in the Chat GPT interface, you get these really boring things where it just tells you some steps that it's doing right now as part of a reasoning process. So this has like a reasoning process baked in where it spends a lot of time reasoning before it, or quote unquote reasoning before it actually solves the task. But on their blog where they talk about what they did, they actually have more interesting, like more complete examples. So this is a ciphertext, and says to decode the ciphertext using the example provided, we'll use the pattern identified plain text decoded as. So decoding, it tells you the decoding method, and it breaks down the ciphertext into pairs. and decodes words. Hang on one second. That's not the one. That's not the one that I was looking for, but there are some examples where it goes in, and it does things like say, that doesn't seem right, or other stuff like this. So it like starts generating, and then it kind of realizes that it doesn't quote, whenever I say realize or any sort of anthropomorphic thing, I mean like under the hood, there's a big neural network calculating probabilities of tokens, but please interpret when I say that into something else. And so the basic interesting thing here is like while generating, I feel like it's essentially learning to self-refine itself. And my guess about how they did this is that they have some sort of search strategy. Maybe it's something like self-refine. Maybe it's something else where they do like a tree search over the possible outputs and try to find the best one. Maybe they do some sort of re-ranking where they generate a whole bunch of outputs and rescore them or something like that. And then they turn this into essentially training data for the model, so the model can kind of like catch itself when it made a mistake during the generation process. So my guess is essentially what they're doing is not is ensemble distillation. It's like ensemble distillation, but it's like maybe search process distillation or something like that, where they do a search process that takes a lot of inference time, and then they turn that into supervised training data here as well. And so the reason why I wanted to mention it here is I do think this is kind of like a version of self-refinement, but it's a version of self-refinement that's like baked into the model instead of something that you kind of have to do as an outer loop outside of the model. So, yeah. Any questions or follow-up or things like that? Yeah.
Can you use a pair of models for refinement, like one model is like a discriminator and the other is?
Can we use a pair of models for refinement where one model is a discriminator and one model's a kind of the generator? Yeah, I think you could definitely do that. I'm trying to think of the best example that I have. Like there definitely are examples. Maybe this is another good example of kind of ensembling methods, but when we know one model is good at one thing and another model is good at other things, then you can combine them together in ways, in interesting ways. So like, for example, the O1 models I've actually found are not like super great at generating code. There are better models at generating code. So you can use the O1 models to kind of come up with a plan or scaffolding and then use another model to like actually generate code. So that's definitely something you can do. Another thing is like, O1 or like Claude or whatever might be kind of expensive to generate outputs. So it's very common for like the big models to be expensive generating outputs. So I could see a world where you also generate output with a cheap model and then critique it with an expensive model or something like that too. So, and I think I've seen a paper or two on something like this, but I can't remember exactly what it's like too. Yeah. Yeah, so I think they have a training data generation process. And this is all conjecture just from like the evidence that's available to us. But I think there's a training data generation process where basically there's a number of ways that you can spend more time at inference time to generate more like accurate responses. So self-refinement is one of them. Like the normal way of generating outputs is you generate an output and you're done, right? But what self-refinement is doing is it's generating the output, then it's running another language model to critique the output, and then it's generating a new output. So it's taking it, 3 times as much compute. Another way you can do it is you can generate 20 outputs, critique them, and generate 20 outputs, critique them, and pick the best one. So that would be another thing. And actually, we have We're not going to talk about this quite as much until like the very end of class, all these inference algorithms. We have a guest lecture by Sean Wellick where he's going to talk about them. But this general idea of like generating lots of outputs and then like distilling from them is one that's been around for a while. So I think that might be something that they're doing. Another thing that they could be doing is they could actually have an explicit search process where they generate like, 50 outputs, prune it down to 5 that look promising, generate more outputs from those 5, and then prune it down to 5 that look promising. So it's kind of like beam search, or there's a method called Monte Carlo tree search that we'll talk about. And if you do something like that, you could find like the absolute best path through them, also including kind of the feedback that you got. So it would generate a first output, and then the feedback would be like, that doesn't look right. It seems that I made a mistake here. And then you could generate another output. So it's essentially baking self-refine into a model, I guess.
In the example, you said that it was in the middle of generating and it said, oops, something else.
Yeah, it can do that. I thought it was on this blog post. Let me look a little bit more carefully to see if I can find it.
I was just wondering why was it in the
Yeah, so the way you could do that is like, look at this. Look at this here, right? You could literally concatenate all of these strings together, and you would get something where it generates an output, and then is critiquing the output, and then generates another output. So treat that as training data, train a model on that, and you get something that will automatically critique itself until it's like done, basically. So yeah. Yeah.
So when it's displaying the result, actually, it's following one branch of the MCTS, for example, and then it's computing all the other branches, and it switches when some other branch, suppose, has a higher score than this, or
So let's say we're doing a tree search algorithm or something like this. That's what you would do normally, but what I believe is in something like O1, they're actually not doing that because that would be very expensive and complicated at test time. So what they're doing instead is at training time of the model, they're doing this expensive search process, and they're using it to generate sequences that kind of have that search process like built into them. So like when it makes a mistake, it will go back and correct the mistake.
so during training though, it would generate before like it goes through the whole process, like generate some text as output.
Yes. Cool.
Are you like teaching it to make mistakes for doing things?
I don't think you'd be, I think you wouldn't necessarily be teaching it to make mistakes, although maybe a little bit you would be, because what you'd want to do is you would want to select the best, you'd want to select the best possible path that you get. So you'd want to select a path that you thought gave a success at the end. And so if the model is capable of succeeding in the very first step, that will give you the best possible path according to, like it being short and getting the correct answer. So in the case where it's possible to get the correct answer right away, that's great, and you just do that. But in the case where it's not possible to get the right answer right away, it's still better to recover from your mistake than it is to.
What if you just take the last?
You could, so this is a great question. Like you could do that, but if you do that, you might be asking the model to be doing too much, basically. Like the model might not even have the computational capacity to do that, right? And that's why chain of thought works also. Yeah.
So this could be part of the pre-training process and not instruction like getting the sequence of the and use it to pre-train.
Yeah, I mean, the actual way they did this is not public, so I'm just guessing. But like, if I were to do this, I would do this after some degree of instruction tuning, because if you don't do any degree of instruction tuning, it wouldn't be able to like answer questions well. So the objective would be to raise the probability of good sequences, and that could be either with just like supervised fine tuning, or it could be with like the reinforcement learning objectives that I talked about in previous classes too. Yeah. Okay, cool. Yeah, thanks everyone. I wanted to link this into something that people are thinking about recently. So that's all for today.